Next up is our session chair, Parvathy Prem. Okay, and she will be talking to us about modeling influence of near-surface temperature gradients on thermal emission from airless bodies, and she is at Johns Hopkins University Applied Physics Lab.
Okay, thank you, co-chair Ian. Okay, so I'm going to try timing myself. We'll see how that goes. But good morning, everyone. What I wanted to do today was to give you an update on some work that I've been doing some modeling work that I've been doing to try and look at how near-surface temperature gradients influence thermal emission from the moon and also from other airless bodies. So this is work that I've been doing with Ben Greenhagen at APL in collaboration with Jessica Arnold, who's down the road at DTM, Kerry Donaldson-Hanna and Neil Bowles at the University of Oxford, and then up the road, Genny To and Tim Gloch at Stony Brook University. And before I begin, I'd just like to acknowledge support from the LRO project through the Diviner team. So our story begins in the strange thermal environment of the lunar Epiregolith, which is that upper millimeter or so of the lunar surface that interacts with remote sensing instruments. And on the moon and other airless bodies, the thermal conductivity of the regolith is typically so low that it can sustain really dramatic subsurface temperature gradients. So for instance, modeling by Henderson and Joukowsky in 1994 showed that under lunar-like conditions, a regolith could sustain differences in temperature as high as 40 to 60 Kelvin over length scales of just hundreds of microns in the upper millimeter or so of the surface. And the reason why this matters is that when we measure surface emission from a body, either from an orbital platform or in the lab, the radiation that we're sensing originates from within this thin layer of finite thickness in which these extreme thermal gradients might exist. And so, as you might expect, when these thermal gradients are present, the emission spectra reflect that subsurface anisothermality. And this is something that's been shown in modeling. It's also been seen in the lab. The two spectra that I have on this slide are from the Oxford lab, from a paper by Kerry Donaldson-Hanna. And they show albite measured under ambient, essentially isothermal conditions, and then under a simulated lunar environment. So you'll notice that those two spectra look very different. And so we'll talk about those differences later on, but what's essentially happening is that different regions of the spectrum are sensitive to different depths within the medium and therefore to different temperatures. And ultimately, understanding the relationship between those subsurface gradients and emission spectra is important when it comes to interpreting remote sensing data sets. But there are also implications for other temperature-sensitive processes, such as those relating to volatile stability and transport. The tool that I've used to generate the results that I'll show you in this presentation is a Monte Carlo spectrum generator. So this is a Monte Carlo radiative transfer model that generates a spectrum by modeling emission from within the shallow subsurface of a planetary body. So I model that shallow subsurface as a series of plane parallel layers, and then I model thermal emission from each of those layers by tracking the propagation of a large number of energy bundles through the medium. So those energy bundles are emitted, they're scattered within the medium, they can also be absorbed. So not all of the energy emitted within each layer makes it out of the medium, but the energy that does escape gets registered as an emission spectrum. There are a number of simplifications that you should keep in mind when you look at these results. One that I want to emphasize is that currently we use scattering and absorption properties that are obtained from a Mie scattering model. So Mie theory does have restricted applicability to closely packed particulate media like a regolith, but at the same time we find that even using Mie theory we do get interesting and useful results. And so the objective of doing this Monte Carlo modeling is essentially to quantify how different depths contribute to a measured emission spectrum. And so if we look at the raw output, if you will, of the Monte Carlo model, we get something like this figure on the left. And so what you're looking at here is what I'll call weight, plotted as a function of wavelength. And the colors indicate depth within the medium. So blue corresponds to the extreme surface, and red is deeper down within the medium. And so this quantity on the y-axis, the weight, is basically nothing but the fraction of energy at a given wavelength that escapes from the medium. And so if you look at the absorption coefficient on this plot right next to it, what you'll notice is that in the more transparent regions of the spectrum, we get more energy escaping the medium and registered in the emissivity spectrum. And so that's something that's very intuitive and easy to understand. The other thing that's interesting to note is that these weights are something that's independent of subsurface temperature. It's simply a function of material properties. So we can do a number of interesting things with these weights. First of all, given a subsurface temperature profile, we can use those weights to generate a radiant spectrum, convert that into an emission spectrum. And the third bullet point there that I want to focus on in the next couple of slides, another interesting thing we can do is, given an emission spectrum, we can use those weights to back out what the subsurface temperature might be. And so what I want to do in the next couple of slides is to walk you through an inverse modeling test case. And so we're going to start with this nominal subsurface temperature profile. We're going to pass it through our Monte Carlo spectrum generator to generate a synthetic emission spectrum. Now, this is for the same enstatite on the previous slide. It looks a little different because it's in terms of brightness temperature rather than emissivity as a function of wavelength. But what we're going to do next is to use this synthetic emission spectrum as an input to the inverse model and see if using this spectrum, we can back out what the temperature profile was. So the inverse model, I won't go into it in too much detail right now, but I'm happy to talk to you in any level of excruciating detail that you would like later on. But it's an iterative process that's based on correlating the brightness temperature at a given wavelength to the subsurface temperature at some depth. And so what I want to focus on, though, is the kind of results that we get from that inverse model. So the black line here is the actual temperature profile corresponding to the emission spectrum that we fed in to the inverse model. The orange line is the inverse modeled temperature profile. And so what you'll notice is that the orange dots line up very well with the actual temperature profile, down to a depth of just between 200 to 300 microns. And what happens below that depth is that we simply don't have enough information to work with. So the emission spectrum doesn't carry equal amounts of information about all depths below the surface. And so that's why the inverse model sort of gracefully fails below this depth of around 300 microns. And we can confirm that by using this orange inverse model temperature profile to generate another brightness temperature spectrum. And so if you compare the input spectrum to the output spectrum in orange, you see that those line up very well despite these discrepancies in the temperature profile. And so that's simply a function of how much information the emission spectrum carries. So this is all working with synthetic data. Something that's a little more interesting and informative to do is to compare how our model looks like when compared to lab data. So on the left here are two lab spectra for enstatite under ambient in blue, simulated lunar environment conditions in red from Donaldson Hanna et al. 2012. And then on the right are two modeled emission spectra, again under isothermal and non-isothermal conditions. And so when you first look at these, there are definitely discrepancies between the lab and the model spectra. But two things I'd like to point out is that at least qualitatively, the model does capture the shift in the location of this emissivity maximum that we call the Christiansen feature, and also the change in spectral contrast when we look at the same material under ambient and simulated lunar conditions. And I want to focus a little bit on the discrepancies here. So these two spectra, the modeled particle size is different than the lab particle size. The optical constants are potentially different. We used optical constants from Rausch et al. And those optical constants, we don't have exactly comparable values, but the composition of that enstatite is a little different from the one that Kerry used in her lab. The scattering parameters, again, were computed using a me assumption. And again, this model temperature profile is not a best fit. And the reason I draw your attention to those discrepancies is that we find that if we look at these sets of spectra slightly differently, they start looking a lot more similar. So what I've done here is to take the ratio of the isothermal, or rather the ratio of the non-isothermal spectrum to the isothermal spectrum in each case. The solid line's the lab data, the dotted line is the model data. And you see that in this case, even though there are still discrepancies, those discrepancies due to these differences in particle size, optical constants, and so on, seem to be sort of masked to some extent if we look at this ratio rather than the raw spectra. So this may be a useful way of looking at these spectra, because in reality, the optical constants of the lunar surface or the surface of an airless body aren't necessarily well characterized. And so by doing these sort of lab comparisons, we can get an idea of how to apply this to real remote sensing data sets. Now, this is for one particular thermal condition. Something else that we're interested in is looking at how spectra change as you vary thermal conditions. And so the way we've tried to do that is by trying to parameterize the influence of thermal gradients. And so the slide is a bit busy, but we'll start on the right here. And so what you have here are 3 different temperature profiles, all described by this equation with the yellow box around it. So this equation is nothing much but a way of describing a temperature profile. There are 3 parameters. There's the temperature at depth, TD, that in these 3 cases we set to 400 Kelvin. There's the surface temperature that we, in this case it's 300 Kelvin, but it can also be varied. And there's this H parameter that describes how rapidly the temperature changes as a function of depth. And so if we look at the spectra that we get using those temperature profiles, this is brightness temperature and effective emissivity as a function of wavelength for different values of H. And the thing to note is that when we have a steeper near-surface thermal gradient, if we look at brightness temperature, that corresponds to higher near-surface temperatures, which lead to higher values of radiance, which translates to higher brightness temperatures. And that increase in brightness temperature as H decreases, or as the thermal gradient becomes steeper near the surface, is more apparent in the more transparent regions of the spectrum. And similarly, if you look at emissivity, you see increased spectral contrast, and you see a shift of the Christiansen feature to shorter wavelengths. Now, you can't really see that here, so I'm just going to zoom in to that portion of the spectrum around 7 to 8 microns in this plot here. And so you can see how, as we go from isothermals to steeper near-surface thermal gradients, the Christiansen feature shifts. And the table simply shows you the modeled position of the Christiansen feature as we change the surface temperature and this value H. And so in practice, this could be useful because we could constrain the temperature at depth through large-scale thermal modeling. We could constrain the surface temperature potentially through inverse modeling, and then maybe we'd only be playing with one free parameter. So just to summarize, Ben and I, our objective here is to develop a set of modeling tools that we can use in various ways to look at the influence of near-surface thermal gradients on emission spectra from airless bodies, both in the lab and on actual airless bodies. So summary of the various ways in which we can play with this. We can quantify the contributions of different depths, inverse model a temperature profile given an emission spectrum. We find that the ratio of the non-isothermal to isothermal spectrum might be a useful way of looking at these sort of measurements. And we also find that steeper near-surface thermal gradients tend to increase the spectral contrast and shift the emissivity maximum to shorter wavelengths. And so just looking ahead here, and I'm running a little over time, but one of the things that we're doing is using more sophisticated means of computing scattering and absorption parameters. So for instance, if you stop by Gen Ito's poster, and Gen is in the back there, wave Gen. Yeah, so that's Gen. Gen has an excellent poster. He does a great job of explaining this as well. But Gen is using the multiple sphere T-matrix method, which models the interaction of an electromagnetic wave with a cluster of spherical particles. If I use those more accurate scattering and absorption properties in the Monte Carlo model, I get spectra, modeled spectra shown in the colored lines, that agree much better with the lab data in black. In the interest of time, I won't go through the rest of the points on there, but you can read those, and I would be happy to take any questions. Thank you.
This is really nice to see, this Monte Carlo modeling. One thing that you may have mentioned that I just didn't catch, In the beginning, the way you set up the layers and the combination of the layers, do you need to make the assumption, which is normally made for these wavelengths, that you're working only with surface properties? You're not working with any transmission?
No, there is transmission. So each of these layers has some absorption coefficient and some scattering coefficient. And so as you propagate the energy, you account for finite amounts of transmission by sort of attenuating that by the absorption.
Okay, so you include both in the sequence that you go through.
Yeah.
Excellent.
I kind of answered one of my questions, but my other question was, so you use your radiative Monte Carlo method to, like in your inverse model, to predict the temperature gradient, and that only works to a certain depth because it's a little bit harder, is what my understanding was from your presentation. But then my question is, could you like shift and instead of, since you know your temperature gradient up to a certain depth, could you look at maybe doing a thermal conduction model after that to continue to predict your gradient?
Yep, sure. So, so for instance, Ashwin Vasavada, Paul Hain, those guys have applied 1D thermal models to the lunar surface. So yeah, you're precisely right. The idea is that below some depth, where these transmission, transparency effects aren't so important, you can use a regular 1D thermal model.
Okay.
And I guess we'll take
sure.
one more question from
Okay.
Yvonne, because it's Yvonne.
Thank you. So I'm just really curious about what you would do next after the plane parallel modeling. What's your plan?
So in terms of modeling accuracy, so one thing that we can do with the Monte Carlo model, so it's essentially gridless, so we're not constrained to plane parallel layers. So something that might be interesting to do is to include some degree of roughness. See how that affects things. And, you know, so for instance, if you look at this Delbo and Bernanke model, they've modeled particulate media as spheres in touch with each other. So maybe we could mimic that by having wavy layers rather than plane parallel layers. And I think Gen's work on more accurate modeling of the fundamental properties is important and exciting as well.
All right, let's thank Parvathy one more time.